Hello everyone, in this lesson we continue our discussion on the bending. Here you see a beam point loaded at the right hand side, pin supported at the left hand side, and at the midst it is roller supported. I did 4 cuts on this beam and placed some soft materials within the cuts so that you can see, so that we can visualize the deformation better, and I believe that it would contribute to our understanding of shear moment diagrams. Let's apply the point load and see how the deformation occurs on the beam. We are applying the point load. Now you see that the deformation, the beam at the tip deflected. You see this shape, and if you look carefully at these soft areas, you will see it is not very clear on the camera. I know on the camera you may not see the differences between these 4 areas, these 4 soft materials. Therefore I will use these 2 sticks in order to increase our vision on the deformation. If I put these 2 sticks on the sections, here the first section, you see the sticks are almost parallel to each other. What does it mean for us? It means there is a very small bending moment on this section. Coming to the next one, also if we talk about the shear force, internal shear force, there is a shear force, but it is much harder to visualize it here because the soft material is not does not easily deform. I will show it here. So this is the small segment, this is the rest. The shear force here is like this. So the right segment is pulling the left segment up. So this is the shear force. Bending moment, if you look at the bending moment, there is very small bending moment here. It is not 0, I know, but it is very small. If we come to the next one, next section, if I keep the sticks next to the edges, you see that now the sticks are even less parallel. Here they were almost parallel, but it is getting less parallel here. In the third one, the situation is worse. The sticks are much less parallel here. They are no longer parallel. You see the V shape clearly. Coming to the last one, they are still not parallel, but this unparalleled situation is not as bad as the one here. See, this is the case in the third one, this is the case in the fourth one. And this one here, they're almost parallel. From this picture, from this deformed shape, and from the soft materials, we can see that the bottom half of these soft materials are squeezed, so it is compressed. if I draw it here, this one is almost parallel. This one, as you might remember from the, so we showed with the sticks here, it is like this. Here it is worse. Here it is again not parallel, but is not as bad as this one. So at the bottom half there is compression. At the top half there is tension. Here compression, tension, compression, tension. Same, but it is very small here. The values are very small in this one. The maximum among these four occurred at this section because the deformation is more. Now if we want to find what the values are, if we say that this load, this point load is 1 Newton, what would be the maximum internal moment and the maximum shear force? So what we can do, the first thing we do, obviously, write down the problem. This is our beam. Point load here, roller support here, and pin support here. And the dimensions between, say this is point A, this is B, this is C. Between pin support and roller support, between A and B, the distance, if I measured with a ruler, it is 15 centimeters, 150 millimeters, it is. Between B and C, it is 13, if I'm not wrong. So, yeah, it is 13 centimeters. Okay, I define the problem here, and I want to find V max, the maximum shear force within the beam, and M max, maximum bending moment. What I do, as you see here, I cut the beam at any section and visualize the deformation. Just like it, I cut the beam here at any section between A and B. These are the discontinuities. A, 1, 2, 3. 3 discontinuities we see on this beam. So we have got two regions. Region 1, AB, region 2, BC. For region AB, I try to find the internal shear and moments. This is segment 1, this is segment 2. Segment 1, segment 2. So I missed one thing. Before starting with the internal forces, I need to find all the external forces. So let's find the external forces first. Here, the external forces, one is a point load. Say this is 1 Newton, and there will be reaction forces here. And this one, if this is upward, if this is downward, this should be upward. If this is upward, this should be downward. In order to find the reaction forces, I need to draw global free body diagram of the beam. So I need to draw the free body diagram of the whole beam. say global free body diagram. There is also RAX here, but it is 0. Why? Because there is no acting, horizontally acting force. Therefore, the reaction will be 0. So we are left with two reaction forces. How do we find it? So the distances we write 130, 150. I can start with a moment equilibrium equation because there are two unknowns vertically. If I take moment about point A, RB times 150 minus 1 times 280 equal to 0. From here RB is equal to 280 divided by 150. It is 1.866 or say 867 Newton. If RB is this, RAY would be from vertical force equilibrium equation. RAY in negative direction, RB is 1.867 and point load is -1. Summation of all these equal to 0. RAY is equal to 0.867 Newton. Okay, I put all these back in here. Now I have got all the external loads. I can continue my segments, working on the segments. On the segment here, the only external load is 0.867 Newton, and the internal loadings here, one will be V in this direction, the other will be a moment. The internal shear force has to be this direction because there is no external force except this, so it should be opposite and equal. Okay, don't forget we always work on the left segment, not right segment, when it comes to drawing shear moment diagrams. Okay, now we have drawn the internal shear force, but what about the moment? What should be the moment? And why do we need moment? We need moment because a green color. Okay, anyway, this is external load of 0.867. This is shear force V. When it is applied on segment 1, what would happen is this. You see that it is rotating, but in fact it is not rotating. Here the beam is loaded, but this segment here, this size of area, is not rotating. If this was loading, it had to be rotated, but it's not rotating. Why? Because this segment, this face of the segment 2, let me show it. The segment 1, segment 2. This segment 1 was trying to rotate, but this face is correcting it by applying a moment. So the moment, what direction should the moment be? It has to be this direction, right? It has to be like this. So it is trying to rotate like this, then it should be something that keeps it in place, like this. So the moment comes from segment 2 upon this face. So the values we show here with red is the values acting on this face, segment 1, and the face where the shear force and the bending moments are calculated. So V here is like this, and the moment here, since it was trying to rotate this, and the internal moment keeps it in the opposite direction, so there is an equilibrium, therefore the moment has to be this way. So there is also a moment. Moment is the result of the resultant of the uneven normal loads here. In part 1 or part 2 I showed that we can show it here as well. In this phase, for example, we said that there's compression, and at the upper half of the face, there is tension. I draw it again. Bottom half, upper half. So tension at the top half, compression at the bottom half. So the resultant of this normal loads is a moment. It is defined as moment for this case, because compression down, tension above. So the moment is like this because it is the motion of this phase, like this. So you see the movement of the segment and this section compressing the half and pulling the compressing the bottom and pulling the top. So the moment is this. And let's calculate what M is. In order to calculate M, I need to give a value for this, or I just say X for this distance. What would be the moment then? We take moment about this point. .867. It is in negative direction, and the force arm is X. V has no effect on the rotation of the segment about this point, and we need to calculate M. We need to put M here, and it is in negative direction as well. Sorry, this one is in positive direction because this is the moment, but moment is trying to rotate this way, therefore it is negative. Summation of them is equal to 0, and therefore M is equal to 0.867x. So it is an equation. As the size of the segment increases, the moment, the internal bending moment increases. But this equation is valid until the next discontinuity, which is point B. So this equation is valid between the regions between the points A and B. The V is constant within this region, and M is linearly increasing within this region. Going to the next segment, next region, BC. This was AB. We do another one for BC. Again, segment 2, segment 1. On segment 1, there is 4.867 Newton. There is 1.867 Newton from roller support. No other external force. There will be internal shear force, and the direction, you guess, it should be downward, and we don't need to write equilibrium equations. We can simply see if this is 1.867, 0.867 here, then this has to be 1 Newton. What about the moment? Again, the moment here, now this time segment 1 is this, segment 2 is this. So it is easier to see here. Actually, you see this side is compressed. We cut somewhere here between this point and this point. Here you see that it is compressed. That means this segment is applying a moment like this. It is doing this motion. Therefore, the moment is in this direction. Now let's calculate moment here, writing the moment equilibrium equation. .867 times the moment arm. Now what is the moment arm? Sorry, force arm. 150 plus x. So we take moment about this point. Take moment about this point, and this force is rotating about this point in positive direction, 0.8, therefore positive 0.867 times 150 plus x. Coming to this is trying to rotate in negative direction, therefore negative 1.867. Force arm is x. What else? 1 Newton has got no effect on rotation. And m, moment, is in negative direction, 0. From here, m is equal to, let me calculate it, 0.867 times 150 is 130. Then 0.867 times x minus 1.867x. Then that means 1x simply. The unit here is Newton, because we use Newton and millimeter. Newton millimeter. Here it was the same. Newton millimeters. Okay, this is the moment equation for the region between point B and C. Now we can draw our shear moment diagrams. Since the page doesn't have enough space, I have to draw the free body diagram on a new paper, because we draw shear and moment diagrams just below the free body diagram of the beam. There was 1 Newton here, 1.867 Newton here, 4.867 Newton here. Okay. This is my shear diagram, and the unit is Newton. So what was V between A and B? A, B, C. Between A and B, the V was equal to 0.867 this direction. That means the shear force is in negative. For shear diagram, this is negative sign convention, therefore I draw it here. I plot the curve, plot the line here, 867 minus, and between B and C, V was equal to 1 Newton and downward, and it is positive for sign convention of shear diagram, therefore I draw it just here. I could plot it here. 1 and this is negative minus 0.867, this is 1, and we complete the lines. Here it is negative, here it is positive. So we completed our shear diagram. What does this shear diagram tell us? Between A and B, the shear is negative. That means the face here is pulled up by the face here, like this. So this is negative shear. And the value between point A and B is 0.867 Newton. Between B and C, well, like this, assume. Between B and C, the shear is positive. What does it mean? This face, because I always say this face because the diagrams are formed on the right section of the left segment. Right face of the left segment. So what is happening here? The shear is downward. This is positive shear, and the magnitude is 1 Newton. Okay, we carry on to the moment diagram. Our unit was Newton millimeter. So what is the moment at the beginning of the beam? It is 0 because there was no moment reaction at point A. If there is no moment reaction, and also if we talk on the equations that we just created, what was the equation between A and B for moment? It was 0.867 x. So if we write when x is 0, moment is 0. So we draw our discontinuities here. Okay. So when x is 0, moment is 0, therefore we start from the origin for the moment, and where will we go? And when x is, what is moment when x is 150? For x equal to 150 millimeters, m is equal to 0.867 times 150. (130 Newton millimeters). So it will be 130 Newton millimeter. But will it be here or here? It will be here. Why? Because the moment we found has got this direction and it is negative. It is negative in general and it is negative in moment diagram. For the moment diagram sign convention, this is negative. Therefore, we need to go down here. Our slope will be downward. Let's say here 150. Sorry, 130 minus 130 Newton millimeter, and it is a slope. It's a linearly decreasing. And next, between B and C, the moment equation was 130 minus 1x, or simply m is equal to 130 minus x. Then when x is equal to 130 millimeters, for x is equal to 130 millimeter. Don't get confused by the x, because x is the x between when x is 0 between B and C, it is here. So 130 is here. M is equal to 130 minus 1 times 130. So m is equal to 0. Therefore, from point B to C, we go like this. How do you know it is a slope? It's a curve. Because there is just this is just a linear equation. Okay, the maximum here, these are 0. The maximum bending moment is 130 Newton millimeter. And what is maximum shear? We found maximum shear as 1 Newton. And it is, sorry, the direction doesn't matter for the internal forces, for the shear in this case. And Mmax, if you want to draw the direction, just draw it. And Mmax has got this direction. So this is how we found the maximum shear and moment values. If we if you look at the beam, deformed beam here, you see that the maximum deformation on the soft materials happened here. Not this one, not this one, definitely not this one. The maximum deformation occurred in this section.